physical quantity is a measurable aspect of any object. For example, if this marker is measured, it has a certain length, it has a certain area of cross section, it has surface area, it has mass, it has volume. All these are its measurable features. This marker itself is not a physical quantity, it is an object. And like any other object, it has certain features that we can measure. Similarly, this board eraser has a certain mass, a certain volume, a certain area, certain surface area. All these are its measurable features. There are certain quantities which we cannot measure, and those are not physical quantities. They are referred to as abstract quantities. For example, our love for something is not exactly measurable, so that is not physical quantity. So physical quantity is a measurable aspect, or feature of an object. Physical quantities are divided into two groups. One group is referred to as base quantities and the other group as derived quantities. Base quantities are 5 in the AS physics syllabus, although there are 7 in all, but 2 of them will be studied in the next year in A2 physics. Base quantities in the AS are mass, length, time, temperature, and electric current. And we also need to know what are the symbols used to express these base units. Mass is always kilogram. Length is always meter. Time is always second, because these are the standard symbols for the SI units, System International units. Temperature is Kelvin, which is capital K, and electric current in ampere, which is capital A. These are familiar symbols for the units. You have been using them in the previous classes. These are not entirely new symbols for you, so you continue using them for these. Derived units, on the other hand, is a long list, and they are quantities like area, which is meter square, volume, which is meter cube, density, which is kilogram per meter cube. You need to understand this one. Kilogram per meter cube is actually based on its definition, mass over volume. That means when I express a quantity in its SI base units, I need to know the equation which is used to define this quantity. This is known as the defining equation for density. If rho is the symbol for density, this equation is the defining equation. So kilogram, I have used kilogram over meter cube. Meter cube is the symbol for volume. So kilogram over meter cube. But this is not how you write the unit. You always express with minus power of minus 3 power of meter. So it is not kilogram slash, this is not allowed. Kilogram followed by a slash and then a meter cube, this is not allowed. Instead, you will always use this form of expression for the physical quantities with appropriate minus powers if they appear in the denominator. Similarly, there is a long list of quantities. You can say speed, which is distance over time, so it is meter per second. You have acceleration. Acceleration is meter per second square, because this is speed over time. Then you have force, which is mass into acceleration. So kilogram into meter per second square. So this list continues, and there are many other derived quantities which can be expressed in terms of the SI base units, and that is actually the exercise to which we are coming now, and that is an important part of this chapter, and we need to understand how various derived quantities are expressed in terms of SI base units. So let's discuss a few more examples of derived quantities. So what we are doing now is we are expressing derived quantities in terms of base quantities. Let's say it is pressure. As I said earlier, in order to be able to express a derived quantity into its base quantities, we need to know the defining equation of pressure. What is the equation that defines pressure? It is pressure is equal to force over area. Force over area. Now, if we know the symbols, the units of force already, force is expressed as kilogram meter per second square, which itself is defined in terms of mass and acceleration. You see, this is mass and this is acceleration. So force F is equal to ma, mass into acceleration. That is simplified to kilogram meter per second square divided by area, which is meter square. So this is all you have to write as the first step, and then you simplify it, and that makes it kilogram m minus 1 s minus 2. This is the final shape, the final form of the SI base units or SI base quantities in which we have expressed pressure. Another example is that of potential difference. Potential difference is defined as work per unit charge in order to move it from one point to another in the circuit. In order to push the charge through a resistance, The battery does some work, and as a result, we have a potential difference across that resistance. And this is the basic, this is the fundamental relationship that defines the voltage or the potential difference. If we define work and charge separately, we can come back to this equation again. Work is force into distance. Force into distance means this is kilogram, this is force, and distance is meter. And when I combine them, this is kilogram meter square s minus 2. This is work. And charge is defined as current multiplied by time in seconds. Current, as I mentioned earlier, is the base unit, and its symbol is capital A, and time is expressed in seconds, and the symbol for that quantity is small s. So that means this is AS with A capital and S small. Now use work and charge in this equation for potential difference in kilogram meter square s minus 2 for work, and charge is AS. When you simplify them all, let's do it on this side. It is kilogram m square A minus 1 and S minus 3. So this is the final expression, the simplified one, with all the powers taken care of, and this is the final shape in which the potential difference may be expressed in terms of the base quantities. This is mass, this is distance squared, this is current with the power minus 1, and time with minus 3. This is potential difference. Let's work a few more quantities, and then we move on to something new. Another quantity which is related, that is electrical resistance. Electrical resistance. Electrical resistance is defined as voltage over current. Now this should be very simple because we have already worked out the units for voltage, the potential difference. They are kg m square A minus 1 S minus 3, and for current they are simply capital A, ampere. And then we simplify them all, they become kilogram meter square A minus 2 S minus 3. So this is for resistance. The name for the resistance we know is ohm. That means 1 ohm is actually made up of all these quantities combined. So ohm is just a special name of this unit, but when expressed in the SI base units, ohm should appear like this. So one more, that is power. Power may be expressed in various, may be defined in various ways, but the most basic one is work over time. Work over time means work that we already know is kilogram meter square S minus 2 divided by time, which is seconds. Simplified, and it becomes kilogram meter square s minus 3. This is power. So what we have learned in this discussion so far is that there are various quantities that we may be required to express in terms of SI base units. And these quantities, when expressed in base units, may not be readily recognizable unless we remember the defining equation, the formula on which they are based, and their symbols. And that is the next task we are going to learn. Sometimes we have to recognize. Sometimes we are given a formula, we are given a relationship, and we have to express an unknown quantity in terms of SI base units. And only after we see the expression that we have to recognize what quantity it is. Let's discuss a few examples of that. Identify. We will identify certain quantities when expressed in SI base units. For example, number one is a quantity which is a product of force and length, and the mass is dividing these two quantities, and then all these are taken under. We need to identify what quantity it is. It's not possible to readily identify it unless we express it in the SI base units, simplify them all, and then it will be easy to see what quantity it is. If I express force into base units, it will be kilogram meter per second square. Length is meter. This is mass, so kilogram, and all this under. This kilogram will get cancelled with this kilogram, and this meter will be squared. This s minus 2 appear as it is, and again under root. And if I see clearly, this is ms minus 1 whole square under root. This square gets cancelled with this root, and I get ms minus 1. Now ms minus 1 is readily recognizable. This is just the speed, because this is distance over time. So what we have learned is that there are situations in which it is not easy to identify a certain physical quantity. If it is a product of various quantities, a combination of various quantities, the technique to identify this quantity is that we express all these quantities into their SI base units, we simplify them, and then in its most simplified form, we can see what quantity it actually is. Another example is that of pressure into volume. It's not easy to see readily what quantity it is. When pressure is multiplied to volume, what quantity do we get? Maybe there are students who have come across a few questions in the previous classes, and they can recall that pressure when multiplied to volume is this quantity. But if they have not done that, it's not easy. So again, the technique is same. We express these quantities in terms of SI base units. So pressure is kilogram m minus 1 s minus 2, as I did earlier, into volume, which means meter cube, and simplified, it becomes kilogram meter square s minus 2. In the quantities I just discussed, the derived quantities, one quantity that I mentioned was work. And these are the SI base units for work. That means when pressure is multiplied by volume, the quantity that this product creates is work. And you see, it is only recognized after we have expressed them in the SI base units. Another example is that of mass multiplied by speed square. When we multiply mass by the square of speed of an object, what quantity is it? Again, it's not easy to recognize unless we express them in SI base units. This is kilogram, this is meter, s minus 1 whole square, and when I further simplify, this is kilogram meter square s minus 2. This is again work or energy. Let me remind you that work and energy have same units. If you write energy here and work here, it is acceptable. Another example could be that of area multiplied by speed. What quantity is it? Again, it's not easily recognizable, but let's see what it comes out to be. Area is meter square and speed is meter per second. So this becomes meter cube per second. What quantity is it? This is known as volume flow rate of a fluid. Volume flow rate. That is showing how much volume of a certain fluid is passing through a pipe, let's say, passing through a pipe or a tube. So how much volume is flowing per second is given by area multiplied by speed. Area here, by the way, is the area of cross section of that pipe, and the speed is the speed of the fluid that is flowing through that pipe. We'll study these kind of things in chapter 4. This is about fluid mechanics. So this is yet another useful aspect of expressing certain quantities in SI base units. One was in which we have discussed a few examples. Those were expressed in their SI base units, and we understood how they are expressed in SI base units. And this is the second useful aspect in which you identify the unknown. There is another way of identifying the unknown quantities. Let me discuss an example or two of that type as well. In that type, we will identify certain unknown quantities given in the formula. So let's see what type of problems we have in the exam. Sometimes they give us an equation and they ask us to identify a certain unknown constant, unknown constant when other quantities, other given quantities are expressed, when other quantities are known and they are expressed in the SI base unit. Let's say we have an equation in which force is related to some constant and there is square of mass and square of distance involved. This is an equation. This is mass is for m is for mass here and r is for distance. This is the force between two masses when they are separated by a certain distance. What is this constant? What are its SI base units? This is the third useful aspect of expressing quantities in SI base units. Let's do it quickly. If I make G the subject of this equation, this F will appear here with R square multiplied to it and square of the mass dividing them. And we can express them in terms of SI base units because this is force. So kilogram meter per second square into, because this is distance, so meter square. Because this is mass, so kilogram square. One thing you have noticed is that sometimes I insist that mass m is this m is for mass, and sometimes I insist that m should be used for distance. This is the usual notation, usual symbol for mass. Sometimes we write a formula in terms of usual symbols, and mass is usually written in terms of m. But you should not confuse this m with this m, because this is always the standard. Mass could be expressed in any other symbol. It could be written capital M, it could be written small m, it could be written even as mu or any other useful or appropriate symbol. But this m is always for meter, and wherever they inform us that a certain quantity is distance, a certain quantity is length, we must express this in m, because that is a meter. So when I simplify them all, this kilogram and this kilogram square simplify to kg minus 1, because this will get cancelled with this, but 1 kilogram will survive, so it goes to the top with -1 sign. M and m square will become m cube, and this s minus 2. So this is the final form in which G has been expressed. So kg minus 1, meter cube, s minus 2. It's not necessary to have a familiar form. This is totally unrecognizable, something different, something new, something we cannot even name. I don't know what unit it is, but that doesn't matter unless your process is correct, unless you have simplified it correctly. Even if it appears to be something unfamiliar, something weird, it's okay. Let's discuss one more example of this type in which an unknown constant is to be expressed in SI base units. Another such formula that we will study in A2 will be force equal to some constant times charge squared divided by the distance squared. This is again a force between two charges when they are separated by a certain distance r. They have charge q, both of them, and the force of attraction or repulsion between them is F. That means this is force again, q is charge. So we know these quantities, r is distance. Once we know the quantities, as I emphasized here, that when other quantities are known, that means we must know the quantities very clearly, and only then we can identify this unknown constant. So force again is kilogram meter per second square is equal to kilogram. This K written as it is. This is charge Ks whole square divided by distance, which is meter square. So now we can simplify it. We can move this m to this side and divide this as. So K becomes the subject of this equation. It becomes kilogram meter cube s minus 2 divided by a square s square. And on further simplifying it, it becomes kilogram meter cube a minus 2 s minus 4. So this time the constant has this combination of base quantities. Again, a very unfamiliar, a totally different, something we don't know what it is, we cannot name it, but that's okay as long as this is correct mathematics. And this is all for today. You can have various exercises of this type in the past papers. Without wasting any time, you can go to the questions in the past papers. You can find these type of questions in the structured as well as in the multiple choice questions, the first or the second question usually of this type. Thank you. We'll have more of it tomorrow.